In this lecture, we will be looking at Taylor series examples, in particular, two classical Taylor series examples. So first, let's recall our definition of a Taylor series. We have a function f with derivatives of all orders throughout some interval containing a. The Taylor series generated by f at x equals a is given as follows. Sum n going from 0 to infinity of the nth derivative of f at a over n factorial times the quantity x minus a to the n. And we see the first several terms are worked out here. Recall this came from the idea that if you could write f as a power series representation at x equals a, this had to be it. If a is 0, for that special case, we call the series the Maclaurin series. So let's derive the Maclaurin series for e to the x. And recall, the key to these is to find the pattern, what's the nth derivative of f evaluated at a, which for a Maclaurin series is 0. Well, we know if our function is e to the x, the first derivative of f is e to the x. The second derivative is e to the x. The 500th derivative is e to the x. Every derivative of this function is e to the x. If we then evaluate that nth derivative at 0, we get e to the 0 or 1. And so that gives us this coefficient for every n. And so our Maclaurin series is thus the sum n goes from 0 to infinity. Recall we have the nth derivative of f at a, in this case is 0, over n factorial times x minus 0, in this case, to the n. Plugging in, we see we have the sum n going from 0 to infinity. We use our result of 1 for that nth derivative of f at 0 over n factorial times x to the n, or more simply, the sum n goes from 0 to infinity, x to the n over n factorial. If we write that out to see what it looks like, when n is 0, we get x to the 0 or 1 over 0 factorial, and remember, 0 factorial is defined to be 1. So we would get 1 over 1, or 1. When n is 1, we get x to the 1 over 1 factorial, or x. When n is 2, we get x squared over 2 factorial, which is 2. When n is 3, we get x cubed over 3 factorial, and then x to the 4th over 4 factorial, plus so on and so forth. So if we can write e to the x as a power series for an interval centered at 0, this is it. So this is our Maclaurin series for e to the x. Well, what's its interval of convergence? Well, we can check that, just like any power series, with the ratio or the root test. Let's take a look at what happens if we use the ratio test. Recall, the ratio test is the limit, as n goes to infinity, of the absolute value of the n plus first term divided by the nth term. In this case, that is the limit, as n goes to infinity, of the absolute value of, let's take each instance of n and change it to n plus 1. So we have x to the n plus 1 over n plus 1 factorial divided by the nth term, which is x to the n over n factorial. And let's simplify and see if we can compute this limit. This is the limit as x goes to infinity. We want to try and cancel some things, so let's pop off one of these x's. Let's rewrite that term in blue as x to the n times x to the 1 using our rules for exponents. And in the bottom, let's pop off the top term from the factorial. So we have n plus 1 times n factorial. And then dividing by this nth term is the same as multiplying by its reciprocal, n factorial over x to the n. And we see the n factorials cancel and the x to the n's cancel. We are left with the limit as n goes to infinity of the absolute value of x over n plus 1. N plus 1 is always positive. Thus, we can rewrite this as the limit as n goes to infinity of 1 over n plus 1 times the absolute value of x. And we note it doesn't matter what you plug in for x. As far as the limit is concerned, x is a constant. Put another way, you can factor that absolute value of x out. And we have the absolute value of x times the limit as n goes to infinity of 1 over n plus 1, and we know that this limit is 0. And for the ratio test, what we care about is for what x is rho less than 1? Well, 0 is always less than 1. So this holds for all x. It didn't matter what we plugged in, any real number. So this means this series converges for any real number. Put another way, its interval of convergence is the entire real line. The result of this, which we will prove with a theorem, with Taylor's theorem in the next lecture, is that e to the x will actually converge to this Taylor series for any x in R. So we've shown that this is the Maclaurin series for e to the x. We've shown that this Maclaurin series converges for any x. We have to show that it equals e to the x. But at this stage, we can state that that is a theorem that it does. And so this is another version of e to the x. It's another way of writing it. Again, the proof requires Taylor's theorem, which is coming. Another example, another standard example, is to look at this for cosine of x. So let's construct the Maclaurin series generated by cosine of x. And of course, we recall the goal here is to find the pattern. What's an expression for the nth derivative of cosine of x evaluated at 0? And so we look at things in terms of these derivatives. So let's work out some derivatives of cosine. We know the first derivative of cosine of x is minus sine of x. The derivative of minus sine of x, well, we know the derivative of sine of x is cosine of x. So we'll have minus cosine of x. The derivative of minus cosine of x is negative sine of x, or sine of x. And the derivative of sine of x is cosine of x. The derivative of cosine of x is minus sine of x. And one key thing to note here is we now have a pattern. We see the 0th and the 4th derivatives match. The 1st and the 5th derivatives match. The 2nd and the 6th derivatives will match. The key thing to recognize is that we have a block of 4. that will repeat. So a repeating block. So once we figure out the pattern for these first four, the 0th, 1st, 2nd, and 3rd derivatives, we then know that that block will just repeat. So now let's plug in. Remember, we have to evaluate these at A. For a Maclaurin series, we know that A equals 0. So let's check the 0th derivative of f at 0. This is cosine of 0 or 1. The first derivative of f at 0 is minus sine of 0. Sine of 0 is 0, so we get 0. The second derivative of f at 0 is minus cosine of 0, which is minus 1. And the third derivative of f at 0 is sine of 0 or 0. And we now see this will be our repeating pattern. When n is 0, we have a coefficient of 1. When n is 1, we get a 0. When n is 2, we get a minus 1. When n is 3, we get a 0. We note that we're going to get zeros when n is odd. So this fn of 0, it's going to be equal to 0 if n is odd. But then we see when n is even, we have to have things alternating. So we have 1 when n is 0, minus 1 when n is 2, 1 when n is 4, minus 1 when n is 6, so on and so forth. So how can we capture that? Well, let's write out some of the terms to try and see what's happening. When n equals 0, we get the 0th derivative, which is just a way of writing f itself, of 0 over 0 factorial, x minus 0 to the 0, which is 1. When n equals 1, the first derivative of f at 0 over 1 factorial, x to the 1. For n equals 2, we have the second derivative of f at 0 over 2 factorial x squared. And for the third term, the third derivative of f at 0 over 3 factorial x cubed. And then we continue, but we noted from our work on the previous page that we have this pattern. We know the 0th derivative at 0 was 1. 0 factorial we can write, because remember, the idea here is to try and identify the pattern. For this term, we know we have a 0 in the numerator. For the n equals 2 term, we had a minus 1. Two factorial x squared. And then for this n equal 3 term, we know we have a 0 again. And remember, this 1, 0, minus 1, 0 pattern repeats as a block of 4. So let's see if we can find a way to write the pattern in sigma notation. Anytime you do these problems, you want to be writing things in sigma notation because that represents the entire series. This sort of thing helps us to get a feel for what's going on and identify the pattern. So what we have is 1 over 0 factorial minus 1 over 2 factorial x squared. Think about your repeating block. The n equal 4 term will have a coefficient of 1 in the numerator and a 4 factorial in the denominator. So we'll get a 1 over 4 factorial x to the 4th. The x to the 5th term will have a 0 as a coefficient. The x to the 6th term will have a minus 1. So we'll get plus negative 1 over 6 factorial x to the 6th. And you can start now to see the next one will have plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial, so on and so forth. So let's write this in sigma notation. Let's start at 0 for n and go to infinity. And first we can see we have an alternating series. So the first term has the plus sign, the second term a minus sign, and it alternates. So we can get that by putting in our minus 1 to the n. So let's check it. When n is 0, we'll get negative 1 to the 0 or 1. When n is 1, we'll get minus 1 to the 1 or minus 1. When n is 2, we'll get minus 1 squared or plus 1. So we capture the alternating sign here. In the denominator, it's not n factorial, but rather 2n factorial. And we can check that. When n is 0, here we get a 0 factorial, which recall is by definition equal to 1. When n is 1, we get a 2 factorial. That matches the second term. When n is 2, we get a 2 times 2 or 4 factorial. When n is 3, we get a 2 times 3 or 6 factorial. So we've captured that. And then notice that the power of n matches the number from the factorial. And we have x to the 2n. And this is the famous Maclaurin series for cosine of x. Now you can also check its interval of convergence using the ratio test, and we'll leave that as an exercise, but the ratio test will confirm that the interval of convergence is the entire real line. Intuitively, the reason for that is this factorial term in the bottom. You have a factorial term in the denominator and a polynomial term in the numerator. And the factorial term races to infinity so much faster than this polynomial term, it doesn't matter what x is. This 2n factorial is racing to infinity so fast that these terms overall are racing to 0 really fast. Fast enough that it doesn't matter what x you put in, you will always get a convergent series. And again, you can check that with the ratio test. And when we study Taylor's theorem, we will see, so Taylor's theorem, which is coming soon, will show us that this actually converges to cosine of x for all x in the real line. And we can state that as a theorem that cosine of x is actually equal to this series for any x. A very similar analysis will confirm that sine of x is equal to this series for any x. And if we write these out, we see cosine of x can be written as 1 plus x squared over 2 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, so on and so forth. And sine of x picks up the odd indexed terms. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, so on and so forth. And again, we require Taylor's theorem to prove this, but these are going to be extremely handy different versions of cosine of x and sine of x. So again, you can think of these as different versions of the same thing. Batman and Bruce Wayne, or Superman and Clark Kent. They are different versions of the same function. We will explore how you can use these very nice, very elegant, and very handy Maclaurin series for cosine of x, sine of x, and e to the x to do many different things. And we will see that in subsequent lectures.